So we are now going deeper into linear programming, and we are looking more carefully, hopefully, into the simplex algorithm. So if you remember from what we ended with this kind of system. I, x1 through m, and here is a coefficient, and then xm plus 1 to xn, the remaining variables, equal b 1 through m. Then we added another row which corresponds to the objective function. So the objective function, which would be minus f, then c whatever m plus 1 through n by these variables are equal f double prime. So it is not bad, but also it is not very useful. You must be saying how this can help me proceed to find the minimum of this problem. So the first step is we will use theorem 4, and this theorem says that a basic feasible solution is an optimal solution with minimum objective function if all, and all is important, cost coefficient c double prime for m plus 1 through n are non-negative or 0. And the proof is not really bad. If you look at the left side at the last row, here it is. So I'm taking a line like this, a bad line. If you take this line alone, here it is, you can see that all these numbers have to be positive. And if we are minimizing, negative coefficient will add to this. So it will take me away from the minimum. Remember that your x's are always equal or greater to 0. So how we would improve? We would improve by taking the objective function and rewriting it as this. So here is the objective function. So I take this side minus f to the other side. I would minus f0 double prime to this side, plus c1 double prime x1 through m, and c double prime for the m plus 1 through m. And the objective function is equal to f double 0 in the case of the basic solution. So what I would do is, to decide the first move, I will identify c double prime that is the minimum of all the c's, okay? And we will use the corresponding xs as a pivot. And if I say if all a double prime 1s through ms are greater or equal 0, the solution is unbounded. If not, I will find a b double prime over a double prime for all a double prime that is greater than 0, which is what we have done in Gauss elimination. Then I will identify R such that b double prime over a double prime is minimum of b double prime of a double prime for all a double primes that are greater than 0. I will use the canonical form by pivoting around a double prime, which is Gauss elimination. So next time we'll see how we can apply this. Thanks a lot.